Okay, thank you. So let me first thank Livia and Tomek and remaining organizers for setting up this wonderful and great workshop. And so I'm going to talk about celestial and Carrollian amplitudes and actually some new development of how these amplitudes can be computed through Liouville theory. So of course you can interrupt me at any time and ask questions if something is unclear. Yeah, that might be because I mhm, return the sound to zero. Um, Now there shouldn't be an echo anymore, right? Mhm. So I put it here and then I get a pointer. Okay, great. Mhm. Okay, thanks. Uh, it's not. Microphone. Okay, anyhow. What is the button for the pointer? So which is the laser pointer? Okay, cool. Oh, okay, that doesn't. Yeah, if you would have a physical one, that would be actually perfect. Yeah, but okay, sorry. So it's about celestial and Carrollian amplitudes. These are amplitudes formulated. I mean, of course, we talk about we are interested in four-dimensional Minkowski space amplitudes. So um, celestial and Carrollian amplitudes are provide a dual formulation of this four-dimensional amplitudes. Wait. In 2 or 3 dimension. And the point is that we have a conformal field theory at hand. And this conformal field theory is supposed to help us to constrain this S matrix um, elements and to use all these powerful methods of conformal field theory to understand or to even derive amplitudes in 4 dimensions. That is the idea. And actually, these amplitudes are sensitive to both UV and IR physics. Therefore, they have a quite different behavior than what you are used to from 4 dimensions. And that's why they also are more sensitive to more powerful constraints on the analytic structure. Can you, I didn't, so in both ways you have yeah, in both you have in both pictures you have both combined UV and IR physics, and this will asymptotic symmetries. I mean, four-dimensional asymptotic symmetries will play an important role for formulating this conformal field theories. And so, as I said, the hope is that we will have a bottom-up approach. Bottom-up approach from 2 or 3 dimensions to 4 dimensions to construct these amplitudes, which then would also be or represent some holographic duals of some flat space-time holography for describing gravitational amplitudes, for example, by some conformal field theory in 2 dimensions or 3 dimensions. So let me first explain what the celestial sphere is or how it emerges. I mean, actually, you see it every night when you look at the sky. Then, I mean, you see all light rays, which so you sit at some specific point and then you see all light rays which can have passed from past infinity at a certain time. But if you wait longer, then of course you see it you see a different set of light rays. Um, so in Penrose diagrams, I mean, uh, which is you have time here and the radius r here. So you might just sit at r is equal to 0, and then you look at the sky, and then you see, for example, these are all light rays which will so you send light rays at a given time, and you see that r is equal to 0, and then these are the light rays which hit at some point, but since it's massless, they travel with the speed of light. I mean, they will they will at some point at some time hit the null infinity, and this is the celestial sphere here. But of course, if you wait a little bit longer, then you are here, and then this is the set of light rays hitting null infinity. And the way how you describe this is you move from the Minkowski metric by a change of coordinates to the Bondi coordinates, to the so-called Bondi metric, and there's as you know from electrodynamics, a retarded and advanced timer. And so here we have the retarded Bondi coordinates, which lead to this picture here. So the U coordinate, which is, so x0 is t, is along here. So it parameterizes this sky plus and sky minus. But you have also the advanced time, and then you have essentially another coordinate slice. Is there some echo or some? That's fine for you? Okay. So you have two coordinate slice, one for retarded time u, and then another one for advanced time. That's bad. I mean, that's actually better in the Carrollian picture, because there you have an you somehow unify these coordinates because you don't have an absolute time anymore. So I will come to this. But so that is how you see the celestial sphere. So this is, I mean, the celestial sphere doesn't live in this TR plane, but it's of course the different direction of the coordinate system. So you see it here for fixed radius, fixed u. That then you have this complex sphere here, which is a celestial sphere here. Z is a complex coordinate, and so it has two real parameters, and so Z bar is given by, I mean, conjugate complex. So in that way, they are not independent, but you have two real parameters. And what is important is this antipodal mapper. So it sends, for example, this point here to that point here. I mean, that is a transformation. But actually, when you look more carefully in this metric, or more precisely at this coordinate transformation, actually you have to send also r to minus r, and then you change here the sign, which means you go from retarded to advanced coordinates, which in other words mean that actually this point is not mapped to that point, which is, of course, you don't see once you sit on the celestial sphere. Then of course it goes here, but actually it goes from here to that point here. And that's, of course, a little bit bad in the celestial picture. And as I said, in the Carrollian picture, this antipodal map is unified in one coordinate slice, because there's no absolute time. In other words, these diagrams are on the same footing. But anyhow, as I said, when you look at the sky at the night, you see all you see the area, or the space, or the set of points in the sky which have emerged at some point and then will hit your eyes. And the same is, of course, for the future. When you send light rays, they will at some point hit the future blaster, sky blaster. That means that means you see that the celestial sphere is a natural arena for defining in outstate of your asymptotic scattering amplitude. So that's the nice picture for or that is why scattering amplitudes really look or seem to be. I mean, the celestial sphere seem to be the right or the right formulation to for massless scattering, because you have this nice picture of the celestial sphere where this particle emerge or disappear. Now, that in a mathematical terms, it means that for any massless particle, which is of course specified by a on-shell form momentum, you can compute the point where it hits the celestial sphere. So this is a simple computation, and it's given by this formula. And now actually this is related to what Matthias asked. So of course, this is a on-shell massless momentum. So it has three independent real coordinate parameters, which we can map now to this one complex coordinate z and another third real variable. So z has two real variables, and then we have omega. But omega is just the energy, so it's a p0 of this momentum, so that we keep for the moment. And so there's a dictionary how to map this point to that point. So by computing this, and on omega is of course just p0. But you can also go back and define by defining this null vector, and then you can express any massless form momentum in terms of the coordinate z in terms of these three parameters. So that's just the basic algebra manipulate. But actually by using this coordinate transformation, you can already see what's going on. That plane waves which are you use to apply when you set up your Feynman rule. So there are eigenstates for the translation operator. So they are good. The translation symmetry is put in manifestly. So that is what are the objects you're used to use in four-dimensional Feynman calculus. But when you transform it, so you insert this p, and then for x you insert this coordinate transformation, which leads you to the Bondi coordinates. You come to this so-called boost eigenstates, which of course are no longer transforming nicely under translation symmetry. So translation symmetry will play a kind of different role in the celestial approach. Are there any questions at this point, or it's too slow? Am I too slow, or it's too trivial, or? Okay. No, we still use plane waves, but when we consider the celestial amplitude, which we will do in a moment, I mean, we should express this p in terms of the coordinate. We want the explicit coordinate dependencies, and then somehow you automatically come to this representation. But you might still use plane waves in that respect. So now on the celestial sphere, so we have this coordinate set, and we can look what Lorentz transformation does. In fact, we could already have imagined what it does, because this Lorentz group in four dimensions is isomorphic to SL2CE. So it is just does this SL2C transformation on the coordinates points on the celestial sphere. That is means that the Lorentz group has a nice representation on as a global conformal symmetry group on the celestial sphere, which so global conformal symmetry means it is created by L minus 1, L0, and L1 by these three generators, and that gives the Lorentz group. And now, as I said, the space-time translations have a different representation. And here you see that they look a little bit quite unusual compared to what you have here for the Lorentz group. So there are these operators and there are these conformal weights, which I haven't yet introduced. So they act on the fields or on the amplitude, on the primary fields, which have some conformal weight h, and that is what they are doing. So at this point, just so we have Lorentz group and we have global spacetime translation, which is of the Poincaré group. And as you know, that this gives you the global BMS symmetry group, which is now manifest on the celestial sphere. But you can also upgrade, or you can also consider the L's of this Virasoro algebra, which are not which are beyond plus minus 1 and 0, and this gives so-called local conformal transformation or super rotations. And similar here, you get local space-time translations. And this is called the local BMS symmetry group. So all these generators can be constructed. I mean, here it's of course simple, but that actually we have constructed. And also this we have constructed. You can construct on the celestial sphere, and you can also, actually they come from certain soft modes of conformal operators of spin 2 and spin 1 fields. And when you also take into account fermions, you can represent, or you can also construct the symmetry generators related to spin 3/2 and spin 1/2 fields, and that gives you this extended super BMS group. Maybe also at that point, let me just make my first reminder what is BMS group. I mean, the BMS group is the group which leaves the group of transformations which leaves all asymptotically flat four-dimensional spacetimes invariant at chi plus minus. So it transforms one asymptotically flat solution to a new inequivalent one. So they can be different away from null infinity, but they represent they leave the invariant what you have at null infinity. So that's exactly where we have our celestial sphere. Or you may also say they're called large diffeomorphisms, which take one asymptotically flat solution to another one. So you don't change the asymptotic behavior of your solutions. But of course, you might change somehow at finite distance your space-time. And we have seen that this global BMS group, which was on the left-hand side of my table, this was Lorentz group plus super translation, but there's more, which is local BMS group, and then even super BMS group, and there's a whole, I mean, there's a lot of results concerning BMS groups by. Good question. Somehow, yeah. Okay, good question. I don't know the answer. Maybe B squared MS or. So it was originally proposed actually to order to investigate the flow of energy at infinity due to propagating gravitational waves. That was when it was introduced. And maybe there were papers before with only one B, or I don't know. So now let me come to my second reminder, which is now what is Carrollian geometry. I mean, very briefly. of course, we all know that when we take the Lorentz group and then C goes to infinite, we get Galilei group. I mean, that's, and Galilei is, so we have our light cones, and then C goes to infinite means that the light cone is in big, is being stretched, and then we have time is absolute. So that's where we are here. So that's also a reference to the Galileo GGI Institute. And but we can do now. I mean, Lévy Leblanc has asked a question: what do we get if you do the opposite? So we send C goes to 0, which gives you another group, which is called Carrollian group, and it's called Carrollian because of this book, Alice in Wonderland. Actually, was strangely just exactly 100 years earlier, and yeah, that was called Carrollian's rule because of it. It refers to this book, and um, well, the book was written by Lewis Carroll, and I mean there are strange things happening in this book, and this is the same thing as this. I think this is the relation. Yeah, I don't know. Maybe it's more deeper this relation. I don't know. I actually haven't never read the book. I mean, I only know this. I mean, there's actually a sculpture in Central Park in no, I think it's the first name. This one, I think it's a double name. Yes. Yes. So now you know why it is called Carrollian. It comes from because of this author, and so that's the opposite what we have in Galilean space-time. So now space is absolute, and that's why what I said before. There's no distinction anymore between the retarded and advanced time, because it's space which is absolute. And okay, I have to say that I was too lazy to draw this, and I took it from a talk by, uh, is it this guy? Mhm. I took it from a talk by Laura Donai. Um, and actually, the Carrollian physics is interesting on its own. I mean, there are a lot of people working on it, and it's actually appears in solid state physics when you consider fractons or in hydrodynamics, and of string theory is interesting on its own, and which also must have a consequence on, for example, double copy structure of closed strings, because you expect some gravity or KLT structure, which is just um, open string squared, but then at infinite tension limit you get something completely different. Yeah. So that is that's actually the important point why this Carrollian geometry might serve as some holographic description of gravity, or of because this BMS group in 4 dimensions, which we mapped, or which we investigated before on the celestial sphere. So then this BMS group was generated by Virasoro and super translation, and then you might also be in 3 dimensions, and then consider this conformal Carrollian group. So there's a Carrollian group which we get from as I showed you before, from sending speed of light to 0 from 4-dimensional Lorentz group, and then you if you take the also the conformal group, you can construct a conformal Carrollian. And so that means this group here, this conformal Carrollian group, um, is as important as the conformal group on the celestial sphere, because it has can equally describe the asymptotic symmetries in 4 dimensions. And so that's why we want to also to consider this Carrollian conformal field theory, or let's say want to investigate this Carrollian conformal field theory. And so it, as I said, it emerges from sending speed of light to 0, which in principle strictly means, when you do it in the Bondi metric I showed you before, means that this you have 0 times du squared, when that we just show. So if you, that's why I actually put here this speed of light here. So that term becomes essentially 0, but you have to do a double scaling limit in order to see what the geometry is. As an exact what? Yes. And so what you will get as a manipulation from a 4-dimensional Bondi metric is that you have the celestial sphere still, there's S2, which is zeta, and you have this null line U, which is the time, or which is the coordinate at scribe plus scribe plus minus. Why you say this? Hmm? Okay, at this point, I anyhow only discuss massless particles, because yeah, I mean, yeah, there will not be, yeah, they will not fit into this space. Yeah, you need to do something, but in addition, but this is the same thing on the celestial sphere, that you describe a priori massless particles, but you can also discuss massive particles by extending the celestial sphere by to some ADS3 space. And now actually we can again look at this BMS group, how it is now represented, realized on this Carrollian space. So Carrollian space is 3-dimensional, U and Z, complex Z. And then this local conformal transformation is represented, the Lorentz group, of course, now has an additional coordinate generator. I mean, coordinate acting on U, differential operator acting on U. So that's, of course, kind of natural to expect. But what you see now is this local spacetime translation, which had a very strange representation on the celestial sphere, now have a nice representation on in this Carrollian space. So that is why people working on Carrollian conformal field theory like more their approach, because they have a nicer representation of space-time translations. Okay, so these are the two spaces, celestial versus Carrollian, and now, okay, I've already mentioned a couple of times that we have conformal field theory behind. So what are the conformal fields or the conformal primaries? And the celestial, so it takes a plane wave, So you express the plane wave, the momentum p in terms of this coordinate I have shown you before. And then you do this Mellin transformation, you integrate out the energy omega, and that is supposed to give you the conformal primary on the celestial sphere. So that gives that can also check then has a sort exactly the conformal transformation, covariant transformation behavior under conformal transformations. I mean, with the conformal weights and so on, and the conformal weights follow from this delta. And in the celestial approach, sorry, in the Carrollian, you define your field. Now, of course, you need fields depending on these three coordinates, or I mean, yeah, z and u, and now you do this, which is a kind of which is not a Mellin but a Fourier transformation. But of course, this you can intertwine between both fields by. So the only difference is this transformation with this delta here, and here you have this coordinate u. So you can intertwine. There's a the integral transformation which maps Carrollian primaries to celestial primaries, or vice versa, which has been pointed out by this people here. In the Carrollian approach. So these are the first papers where they computed Carrollian amplitudes. So yes, yeah. Yeah. Yeah, you can do yeah. So here you have a space in the delta space. You and so this is a complex variable, and in the delta space you can obtain this u dependences by through a integral transform. I mean, so in other words, here you don't. In both cases, you have here. So here you have this coordinate z and z bar and delta, and here you have z and z bar and u. So you don't lose information by doing this in the. That is here, yeah. That is the delta is it's h plus h bar. It's h plus h bar. And which then the h is described as a conformal transformation works acts. And here actually I don't, I have to look it up. I don't know it by heart. I think so, yeah. I think so that it's combined. It's more complicated, yeah. So I will actually yes. So of course this is now I mean celestial conformal field theory and Carrollian conformal field theory are not standard conformal field theories which you are used to use. So we need to understand them. I mean, in other words, I mean, when you talk about conformal field theory, you take this book and then everything is written there. But if you talk about these are standard conformal field theories here, like minimal models, and but when you talk about this, you have to, let's say, to write this book completely new because these are non-standard conformal field theories. So you have to define what are operator product expansions, how do they look like, what is the energy momentum tensor, and okay, Virasoro algebra I have shown you how it is represented on the celestial amplitude, and what is conformal block expansion, and so on. So that actually there has been a lot of results also from our group and also Harvard group particular on the celestial side to derive this. And actually, I will show you in a moment a sample of how operator product expansions look like. But actually, on the Carrollian side, there's even less known than on the on the celestial side. Um, and actually, what we recently have derived is that at least there are some KC type differential equations which allow us to construct or to derive compute amplitudes from differential equations, and they actually unify this. Because I mean, differential equations are always nice, and if they have a particular structure like this Knizia-Samologikov type, I mean, then they're especially nice, and then that is what I will also show you in a moment, this differential equation. But now, as I promised you, so why is this conformal field series so different, both on Celeste and Carrollian than what we are used to now from this orange book? As I mean, here's operator product expansion, for example, between two Kluon operators of so they have this conformal dimension delta 1, delta 2, and this is the spin, so plus 1, plus 1. Huh? And then, okay, this is what you expect for this field, Z minus W. So these are the coordinates on the celestial sphere. And then, yeah, you have another operator, another Kluon operator of this form plus regular terms. And this has been derived by these two groups by different methods. But actually, what's nice is this beta function here that looks a little bit stringy here. I mean, so there's that whenever you see a beta function, I mean, you might have string theory in mind. So this is really the beta function, the Euler beta function, which appears here. And now doing it also on the celestial, on the Carrollian geometry or Carrollian space. So then you have three coordinates. Then it looks even more complicated. That has been only recently derived by these three people, and actually it's even also singular when you have when the spin is 1. So when J is 1, then there may are even singular terms, but that you can cure by just take a derivative, which is means okay, color index A, B, C, and this is structure constant. So thank you. Yeah. So yeah, this is color index, and yeah, and here it's just for some or some arbitrary fields with spin J1 and spin 2, and then this fuses into this states sum or linear combination of states. Yeah, if you would here have plus and minus 1, you would also have yeah, it's plus so it's kind of holomorphic sector. Yeah. Yeah, but actually, if you would have minus 1, then yeah, you would have plus with minus here. Yeah, then you would have also anti-holomorphic. You mean minus with minus is anti-holomorphic. It would have a mixture of holomorphic and anti-holomorphic. No. Well, but it's kind of regulated. It is Z bar minus W bar over Z minus W, which is kind of subleading to this. So that is so to say it's less singular than plus plus and minus minus. So if in other words, one again plus minus would involve Z bar minus W bar over Z minus W. Now let's eventually consider amplitudes. So celestial and Carrollian amplitudes. So this is a generic form of an endpoint amplitude. I mean, 2 to n in four-dimensional space-time. So we have this delta function, moment conserving delta function, and there's, of course, some polarization dependence epsilon and an external momenta p. And now, as I said already, obtaining this conformal primaries from the plane wave, for example, is by applying this Mellin transformations. So that means now we first write this amplitude in terms of celestial coordinates, omega and z's. Of course, now each of the particles' external momenta has its own position on the celestial sphere Ci. And then, so we just rewrite it in terms of celestial coordinates and do this n-fold Mellin transform. So that is the prescription how to obtain the Mellin and the celestial amplitude. So this is top down. So you're in 4 dimensions and you derive this amplitude. So it's in principle not much. You don't gain yet so much information about the 4-dimensional physics, because you just take the 4-dimensional results and transform it down to 2 dimensions. Similar now in 3 dimensions, Carrollian. You have now this transformation which we introduced before to obtain the Carrollian conformal primary fields. And so the message is that now here you have a celestial amplitude depending, of course, on the coordinates of the celestial sphere and this conformal dimensions delta. And here you have Carrollian amplitudes which depend on these 3 coordinates. So this is, at this point, just a takeaway. And now also some very simple samples, these amplitudes. So let's start with a 2-point amplitude. This is 2-point amplitude in 4-dimensional Minkowski space, but we simply write it in terms of celestial coordinates. So we have this dictionary, and then of course we have a 4-dimensional delta function, which is p1 plus p2 is equal to 0, and then we insert these coordinates and have some Jacobian, and that is why we have this omega. This is now comes from the 4-dimensional delta function. So this is still the 4-dimensional amplitude. Now we do the Mellin transformation and get the celestial amplitude, and we get, so that is now already the thing we have to observe or to acknowledge, that these amplitudes, this celestial amplitudes. So by the way, there's a comma missing. So the celestial amplitudes are functions on the celestial coordinates, but they always involve these delta functions. And they actually will become even, as we'll see in a moment, will become even worse when you have higher point amplitudes, because then holomorphic and anti-holomorphic coordinates will be mixed. Sets. And this is a Carrollian amplitude. You see the Carrollian looks already, it has involves some IR divergences, which need to be regulated with this regulated beta. So it's even more complicated. So this reference is referred to this Carrollian amplitudes. So this is probably has been first derived by Strominger and al. But it's so you can again, this is just some method to cure this singularities. You can, of course, consider so-called Carrollian descent. This is act with this operator, and then, for example, by that you kill this regulator term. So that's the way how you might get, or how you can get nicer amplitudes. And this is the same thing as I said before. These amplitudes are related through through inverse Mellin, and so you can do inverse Mellin on that, and then you do Fourier, and then you come from here to here. So they're interrelated. So you can always switch between the two pictures, kind of. Now it comes the more interesting amplitudes, which are the 4-point amplitudes, of course. This is the 4-clone amplitude, so there's the MHV amplitude only, and this is the non-vanishing MHV amplitude. So 2 minus clones and 1 plus, 2 plus. And then you see that already. So what the takeaway is here, that R is a cross ratio on the celestial sphere. So this is Z1 minus Z2. So this is this position, and you have this you have this delta function which mixes holomorphic and anti-holomorphic coordinates. So this is bad because this clearly tells you that we are talking about non-standard conformal field theories where conformal block to composition works differently because you have this mixing of holomorphic and anti-holomorphic coordinates. And we have then 1 year later computed the graviton amplitude. So this is the graviton for the MHV for graviton amplitude in the conformal basis. And um, yeah, so this is you see it has nice forms. Both both amplitudes have nice forms. They have this characteristic Ci minus Cj terms, products, and with conformal dimension h over 3. So this is exactly what you know from the orange book, and it's similar here for the gravitational amplitude. But they have this delta function. But on another hand, what's also kind of interesting is that they look very much similar. So there's not so much distinction between gravitational and clone amplitudes, except essentially this delta function arguments here. Hmm? Yes, it's a good question. So there's in principle, because if you're sitting on the so-called principal series, this deltas have to sum up to 1, which means so you fulfill the delta function, while here you don't. So that is a singularity because if you put a 4 here, I mean you're not on 0, but you can make use of it in the distributional sense. So as a distribution, it's a perfect valid amplitude. Mm-hmm. Beta is the sum over these deltas. Yeah, thank you. So beta is sum of these deltas. It's kind of definitely. Yeah, I should. Huh? Yeah, all 4. Mm-hmm. All 4. Yeah. Sorry. Yeah, that's a good point. Yeah. Thank you. Yeah. Mm-hmm. Mm-hmm. On the celestial, exactly. Yes. 4 these conformal primaries. Mm-hmm. Yes. No, it's crossing symmetry on the 2-dimensional celestial sphere, which is not a priori related to 4-dimensional crossing symmetry. The origin of the 2-dimensional crossing. Well, you can do like r goes to 1 or r goes to infinity, or that gives you here the limits. That gives you that describes so you can define an channel on a 2-dimensional celestial sphere by r goes to 0 or r goes to 1 or r goes to infinite. So then means you do something on this um, celestial coordinates, like C1 goes to C2. But like 4-dimensional crossing symmetry is um, Yes, yes. Which relates to the two-dimensional. Uh, uh, um, um, it could be, I don't know at the moment. Would would be, I have to think about it. I mean, but yeah, I will tell you. Yeah, sorry. I mean, I could be. Um, okay, so that was actually the question that about this divergence that you have in principle here, UV divergence, which comes. So you do four times Mellin transformation. And when you do the last one, you have this integral essentially, and then which for gauge amplitude is finite, but for gravity, this is one, and then you have this UV divergence occurs, but it will be, this is the integral which exactly gives you the delta function here. So that means in the distributional sense, it's uh, perfect fine amplitude. So in fact, when I mean I had already, this is now by now old result. So there are always people asking why you perform this amplitude. So you cannot discuss um, um, gravity amplitudes in a conformal theory. But when you do distributions, I mean, then so in the distributional sense, it makes perfect sense. And indeed, what you why this amplitude is interesting, because you can discuss soft limits. So you do something with the deltas, sending delta to 0, 1, or -1. This will describe like this would be now beyond the scope, but I can tell you that sending deltas to 0 or negative integers are related to soft or subleading soft theorems. And so that means you can here, by sending delta to certain minus objects, you can reach this value where this integral is finite. So that means you can use this amplitude. You can use this amplitude and discuss soft limits, which are of course perfectly well defined objects. Hmm? From delta from 1, everything on the left-hand side in the complex plane, 1, 0. I mean, but of course also real numbers. But so it's so 1 is called the principal series, and then everything below. But in principle, by analytic continuation, you can also allow for the right-hand side. But this gives you the soft modes going left-hand side on of delta is equal to 1. So left-hand side of principal series. Now, just as an sample, I mean, how does a Carrollian 4-point amplitude look like? And I have here I have to admit that we didn't compute Carrollian amplitudes with we were not the first computing Carrollian gravitational amplitudes. They have been computed by these people end of last year. So, but what we did then is actually we computed Einstein-Young-Mills amplitude. So one, for example, one, and that's why I show you a sample of this sort, because it's what we did. So it's one graviton amplitude with minus minus and two gluons, and it's just a sample, so it looks of course complicated. There's also this delta function and has this coordinate. So it's a function on depending on celestial coordinates z and Carrollian coordinates u. Mhm. Yeah, that you can ask exactly the same question, right? Yeah. Yes, but already for this, I can already tell you that we know so little about three-dimensional Carrollian conformal field theory that the answer is by sure not now. But two, for the question of two-dimensional crossing symmetry versus four-dimensional, I'm happy to. Mhm. Mhm. And I don't think so because of this delta function, mainly. Because I mix this because you have this holomorphic anti-holomorphic mixing. But why should conformal blocks be the same? I mean, you have, but the state, you have different states. Mhm. Okay, good. Let's wrap up now. So these amplitudes have many delta functions. I mean, the four-dimensional case is R minus R bar, so which R being the cross ratio. So there is a mixing between holomorphic and anti-holomorphic sectors. This means that you have non-standard conformal field series in 2 and 3 dimensions. Um, and um, um, and of course, what you're now what we are now from minimal models or Wessel-Minowitten models and so on is that we have the standard conformal field theory, and then 2 and 3 point correlation functions are determined by conformal invariant, and then 4-point correlators are constructed from by solutions of partial differential equations, in particular Knizia-Zabolodzhikov type equations. And this is what we want to adapt or want to see whether we can have something similar for this conformal field series. So that means we want to have something similar as here, that 4-point celestial correlators and also Carrollian correlators are constructed from solutions to PDEs. And what are these PDEs? Um, Now, actually, you can, without any reference to Celeste or Carrollian, you can look at your endpoint amplitude and introduce a BCFW on two particles, I and I plus one, and then you can look at the amplitude, how it behaves under this Z shift, as this BCFW shift. And the behavior can be described as a differential operator. And then when you just look at the first order, you get an equation, and the first order of the equation gives us this differential equation. I mean, that has been found by Anastasia et al. And now you can say what does this differential equation mean in the celestial sphere. Yeah, you just I mean, you just transform it into the celestial coordinate and you get this. And that is actually now what looks very much like a KC type equation. Actually, in the Carrollian picture, it looks more, that is again this strange exponential which come from this, that because momentum, because of your momentum, that you don't work, that your momentum, that translation invariance is, or translations are represented by these operators, which act in a non-trivial way on your fields. In other words, if you don't actually, that is the way how this has been found, this differential equation, it was before this. So as I looked at consistency conditions of celestial operator product expansions and derived some null state condition. I mean, you know from conformal field theory, null state conditions. So you have a consider a correlation function with a null state gives you a differential equation because you have a null state, which is a combination of some Virasoro operators, making it zero, and that gives you a differential equation. And you setting up a similar null state condition gives you this differential equation. So we have some nice differential equations for endpoint amplitudes in celestial conformal field theory, and actually we can ask the same question, whether we have a similar KC type equation in Carrollian geometry, and yes, we have. But I will show you also it. But now let's about extension. Loops haven't been discussed yet, really. No, I think that should be also possible in by going to unit to the cuts. Probably should. I think you can should be able to upgrade it to a loop equation, I think. And yeah, that's tree level. Yeah. Everything what I'm saying today, except yeah, is tree level software. Yeah. But you're right. I think it would be interesting to see what is how this, or whether this holds also at loop level. Um, so now we solve this differential equation. Um, for clone amplitude, and what we get is the following form. So we now write our solution in this form such that it looks like what you expect from a clone correlator. So we have this so-called gauge sector, and we have some let's say some universal integral or some universal function. So I mean that's coordinates on the celestial sphere. And okay, so we have there's a whole, since you have a differential equation, there's a whole class of solution. You can classify the solution by writing the solution in the following form. So you have here this of course resembles the Mellin transforms, and you can I will show you in a moment why how this is related. So you can classify the solution of your differential equation by saying that you have that they solve for clone amplitudes in the presence of a dilaton field. So you have this dilaton field or this dilaton source introduced with this J, and then there's a plane wave factor for the dilaton, and that this object is the solution, or this solution can be parameterized in terms of this integral. It will become more clear in a moment, but this is for the moment. But already here, I could say that, or I should say that these solutions of this KC type equation are very much reminiscent of what we know from Coulomb gas formulation of minimal models, where correlators vanish in the absence of a background charge, and the dilaton to some extent will now serve as the role of this background charge. Mhm. Mhm. With the delta function, with this, mhm. Because now we don't look, so we forget about the celestial for clone amplitude, because we don't like it because it has this delta function. Yeah, so this is for clone amplitude, and now we, so to say, we don't like it because it has this delta function, so we don't. It's difficult to do conformal block decomposition and many other things. So. And now we say, can we look at something which mimics the properties of this clone amplitude? So we go one step up backwards and set up this differential equation. So this differential equation is more general. Is more general. No, it gives, yeah, it can give you also a clone amplitude, but so you can, it has a solution which which is a celestial clone amplitude involving this delta function. So this is a particular solution. But we can also, in other words, the solution I have, I write here parameterizing which parameterized solution. I can also choose a J such that it mimics this delta function, describing the really the clone amplitude you know from 4 dimensions. Mm-hmm. Yeah, that is because we have this field. So we have this field, so that the fact what we have, that we have minus, plus, and so on, means that we choose here these spins of the particles j plus minus 1 and so on, and then solve it. Get of course, because it's a differential equation, we get many solutions, but we throw away the solution which gives us the original clone amplitude, because it is, so of course it must be solved by it, because of we have started here for. So this is also solved by the Park-Taylor. In other words, this is solved by Park-Taylor amplitude, but it's solved also by other amplitudes. And these other amplitudes we say are nicer because they don't have this delta function. And they correspond to amplitudes which have a dilaton in addition. And I will be more precise to it. So the generic class can be written like that. And then they have this dilaton background, which in principle resembles also what we do in minimal models, where we also have a background charge in order to have a non-vanishing correlator. And now I come to the new part, that I will tell you that this amplitudes with this dilaton background, that they can correspond to, or they can be derived from Liouville conformal field theory. But let me first, okay, since time is unexpectedly running fast, let me, though you can do the same thing for Carrollian amplitude, so you get a nice differential equation. Actually, that was also our last paper. So that you see here, it's nicely, it's more, it looks, it doesn't have this exponential, it's KC type equation, and actually has some nice solutions which are called electrical magnetic solutions. So the magnetic solutions don't have this delta functions, while the electric have one. So here you see, like, you can have solutions which have this original delta functions. We are now from celestial clone amplitudes. But you see, you can also have other solutions which don't have delta functions. So this is the Carrollian side. And now let's come to celestial Liouville theory. So I tell you now that by taking particular solutions of this KC type equation, we can describe by Liouville theory. And this gives you then the promised bottom-up approach that forget about 4-dimensional clone dynamics and whatever. I mean, you just take your Liouville theory in 2 dimensions and compute amplitudes, and then actually you can even compute one loop, and the one loop actually happens to agree with the one loop in 4 dimensions. That is actually a very non-trivial result from last year. So what is Liouville theory? Liouville theory, you have a conformal field phi, and you have this Lagrangian. And Liouville theory has a background charge, which is can be parameterized by this real number b, and a central charge then is computed the following way. And you have primary fields which are constructed from this phi as this exponentials. And in fact, what our Liouville theory is at tree level, or what we need at tree level is that we look at this infinite central charge limit. So we take B goes to 0, so then this becomes infinite, and this limit gives the tree level result. So in this Liouville theory on its own, you can, as usual, construct correlation functions of this primary fields. And as is implied by here, you need to saturate or supply a background charge in order to make these correlators non-vanishing. So that means you cannot just take n of these fields, but you need in addition a field which an operator which supplies the correct background charge. So let's see whether this does. So let's count the total charge here. So it's 1 over p and the sum of these alphas. And if this alpha i's would fulfill this condition, then so that means this is p. This gives exactly q. So then everything would be fine. And as I said, so this is a conformal dimension of this field. So this is how it is computed, and we are interested in this p goes to 0 limit, which is the infinite central charge limit. But then in that limit, this correlation functions are complicated objects. They have been first computed by Dawn Otto and then further analyzed by Samologikov and Teschner and so on. But when you take this expansion b goes to 0, they take a simpler form, and then they can they give you nice expressions. And indeed, you can now, that is what we did, you can take this integrals. So this is, you do this correlator gives you this. So this is the Liouville theory. And now you take it and you can rewrite it in the following form by using Duffin's embedding formalism. You can write it in terms of this integral, which already looks like a multiple Mellin transform, known from celestial amplitudes. Okay, this is just an identity. So this integral I showed you before, after some tedious computations. So this integral here, this factor here, can be as follows. Now, you can all, I showed you before the solutions of these differential equations, the general solutions, which can be classified by this Dilaton background J. So you can see already that now this Liouville correlator has a very much the same form as what we find as our solutions, namely just, so how can you match this? Take this source, and then this is exactly the same. In other words, if the Dilaton source, so I mean, when you look at the Dilaton source, so Klein-Gordon equation is equal to J, so it corresponds to a shock wave of the Dilaton. Then this solution of our KC type equation, celestial KC type equation, is exactly the Liouville correlator, and this is also for any number of gluons. Now, okay, let's go one step backwards, and I mean, do some basics. I mean, so what is Dilaton Young-Mills theory? I mean, so you have Young-Mills, and you couple it you couple a Dilaton to Young-Mills field strength in the following way, and here you have this coordinates J, and then looking at amplitudes, MHV amplitudes, MHV clone amplitudes in this Dilaton background means that you couple this Dilaton through the source, and in other words, the moment, you don't fulfill any more moment conservation for the Dilaton, but now the total moment is taken away from the dilaton source Q. So you couple this by a propagator 1 over Q squared, and then you have the source here. If you compute these amplitudes in this background, this has been done by these people. Actually, they take exactly the same form as Park-Taylor amplitudes. But of course, momentum conservation is no longer is fulfilled in this way. It's Q, yeah. So it's yeah. Q is no, but Q is not fixed, not fixed, yeah. So okay, this is now you can compute the celestial now you can compute the celestial amplitude of this object. I mean, this is the usual way that you do that so that is the way how you couple this amplitude to the dilaton background. So you have this propagator and the source, which in our case the source is one, because that in the Fourier space leads to this delta function in four-dimensional space-time. And so the upshot is, if you do this, if you compute this integral, you get exactly what is here. So in other words, now let's summarize. What we have now is that we consider gluon amplitudes, celestial gluon amplitudes, and they can be described as this partial differential equation. And we look at a particular solution characterized by some current factor times some universal, let's say, Dotzenker-Fadev-like complex integral. And then this object can be computed by Liouville theory. So it's given by some correlation functions in Liouville theory. So that is the exercise I showed you before. So it computes this correlation function in Liouville theory. So you need an extra operator to saturate, so to get the right background charge. It looks like a Cooper-Nielsen-like type of, or Shapiro-Virasoro type integral. And then do this integral, it can be rewritten and looks like this dilaton, this amplitude in dilaton background. And then you have this additional gauge current factor, which is standard, let's say, looks like from a standard gauge current algebra you're, for example, now from heterotic string theory. Actually, it's a bit non-standard because you have this currents, but this has been also recently discussed in this current algebra by Pasquet and Costello. So this is the setup, or this is now the prescription how we should obtain the celestial amplitude by just computed in a Liouville theory. So, or in words, the celestial Young-Mills amplitude but we have this presence of the dilaton background, is a correlation function of primary fields in Liouville theory, which are these light operators because B goes to 0 times this holomorphic current factors. Now you can say this might be just an accident, or it may have been just tuned like that it happens to agree. So I have said that this is then the B goes to 0 limit, which corresponds to large background charge Q. And now you can look what is the next order in B, which is B squared. What do they describe? In fact, they exactly describe the one loop correction in this dilaton, in this amplitude in the dilaton background. So we have computed last year this first order correction to this dilaton background in Liouville. So we took the Liouville correlators and expanded this complicated object of Dorn Otto to second order in this background B, and then took this object as our bottom for describing this clue amplitude ground. Then we transformed it back, and this is a tree-level contribution we discussed before, and then it gives you this one loop log terms, which is exactly when you do this identification with the one loop parameter in the Delatone one loop setup, gives you exactly the one loop correction. No, it's not a loop integral. I mean, it's this background, so it's an expansion in this background B. In principle, it should be possible to trace it back and see what is describing the loop integral of the four-dimensional theory in the Liouville. This is intriguing because at the beginning of my talk, I have stressed a lot that that this celestial program is very much tied to asymptotic symmetries. I mean, because these are the symmetries you see on the celestial sphere, which likewise is related to IR physics. But now you suddenly also, by looking at this conformal conformal field theory of celestial sphere, you also seem to probe UV physics. This is striking. In fact, when we had this last year out, I mean, then in spring, I mean, this Harvard group, they also then took this Liouville result, our Liouville results. I mean, I think it's one can say it like that. And yeah, did also some. I mean, essentially did re-derived our tree-level results. And but actually, it's getting more and more interesting because now very recently it has been also described for gravitational amplitudes. So the gravitational amplitudes seem also to have this Liouville description, and yeah, we are. I mean, so this group, we are now actually trying to work out what these higher order corrections are describing, going beyond b squared, and so this is quite seems to be quite interesting now. What's going on there? Now, yeah, strings on celestial sphere is not. I mean, yeah. Well, depending on what you like, what you think about string theory, you might find it interesting or not. But yeah, but the point is, in principle, that you might always ask a question: is the string worldsheet somehow related to the celestial sphere? And actually, we found, at least in this infinite tension limit, actually, these points on the string worldsheet are exactly the points on the celestial sphere. So there seems to be a correspondence. And actually, yesterday, Matthias asked me about whether in this Liouville picture you have a similar correspondence between the worldsheet you have in Liouville theory and the celestial sphere. And actually, you need to do, then I thought about it, and I think you need to do some similar limits, and at least in a similar region, in a similar high energy region, you can match the points on the Liouville sphere to the point on the celestial sphere. And then, of course, the question is how you, in other words, the worldsheet vertex operator position in Liouville are then points on the celestial sphere, same way as here. But of course, the question, actually, I gave it to my master student now to see what, I mean, not this question here, how the string worldsheets, or how you go away from this point, can you compute some sub-leading contributions and see to what extent this picture changes this correspondence between worldsheet and celestial sphere. And but actually, Matthias, I realized it's even more interesting to discuss or answer this question in Liouville theory. I think it's so that here we found this correspondences between string worldsheet points and celestial sphere in this infinite energy limit. And okay, I gave it to my a couple of months ago. I gave it to my master students that we should discuss how this behaves when you go away from this limit. But actually, the question seems to be more interesting to do this in Liouville theory because to somehow relate the celestial sphere points and then to some worldsheet vertex operator positions on the Liouville target space. So yeah, then because this then would give then at least in strings you have a free world JIT CFT might give you some more information about this celestial conformal field theory. Okay, let me conclude. Let me conclude. So I have shown you some unifying picture of celestial and Carrollian amplitudes. At the level of differential equations, which are KC type like, and they can be solved, for example, such that they describe amplitudes in non-trivial backgrounds, which after all is probably what you should do, because when you do string theory, I mean, and you extract gluon amplitudes from string theory, you always have a dilaton in addition. So so in principle, from string point of view, it's quite natural to consider gluon amplitudes in a dilaton background. And then, so let's say most of the results in celestial picture is top down. So you have your results in 4 dimensions, you transform them to 2 dimensions, and then you might learn things about this celestial conformal field theory, but you don't learn anything new for the 4-dimensional theory. But the interesting part is whether you can learn something, whether you can go bottom up, whether you can have something completely radical new, like this Liouville theory for Young-Mills amplitudes, and then do computations in 2-dimensional Liouville theory and get something new, some new results or some new informations for your 4-dimensional theory. And actually, when you talk about Liouville theory, a bell should ring about HET. I mean, Aldai Gayoto Takinaga correspondences between Liouville non-perturbative super Young-Mills. So that's maybe even related that. So they have expressed Seiberg-Witten instanton corrections to Liouville correlators, and that might be even fantastic. Actually, we have started to think up to do some computation to relate this Liouville objects of HET to the celestial approach. So it might be even that there's some correspondence between non-perturbative super Young-Mills and B-level super Young-Mills. Eventually, this might help to understand flat space-time limit of ADS-CFT, which is, of course, the ultimate or one of the really um, um, most striking questions. And thank you, yeah. Um, no, no, I mean, um, I mean, we don't see a celestial torus, so to say, or higher genus surfaces, but um, I mean, it might be. I think it might be also that this genus expansion in string theory is not really the right way to look at it. So um, celestial sphere versus sphere. Yeah, it's like similar is what you have from with scattering equations that you match points on the sphere. No, no. There's not. No, no, not. But yeah, it would be interesting question. Yeah. Yeah.